said that we start talking about real waves. And I described a typical record of real waves. Elevation or water surface elevation. As being a mixture of different kinds of waves. And I defined a couple of terms. The significant wave height, which we call H sub S, is the average of highest 1/3 of waves. And then the period probably I should call it an average period or a significant period. Stay with this. Is the number of up crossings. I'm sorry. The time divided by the number of up crossings. In the wave. And the up crossings were marked off as complete wave cycles. So the idea is to get a significant period, you take a sufficient number of waves, typically about 15 if you're interested in short-term measurements, and determine the time over which they were taken. And the period is just the significant period is just the average period of the wave. In order to go further in describing something like this, we need to be able to describe a distribution, some kind of a distribution that's descriptive of the whole thing. And it's been found that the cumulative Rayleigh distribution fits waves pretty well. You all remember Rayleigh. The man who talks about dispersion in the atmosphere and waves in general. His assumption. And cumulative Rayleigh distribution looks something like this. The probability that the height of the wave is greater than some selected height, I'll call it H hat, is equal to exponent minus H hat over H RMS squared. This probability that n H is greater than H hat, I'm sorry, H greater than H hat. Is the number of waves higher than H, I'll call it little n, divided by the total number of waves, same n that we use here. And HRMS, root mean square, is just what you'd expect for a root mean square. It's the square root of the mean of the waves. So the J's goes from 1 to n. And it's times H, J, divided by n. You're all familiar with root mean square for electricity and magnetism, for example. I recall that we have the energy for waves, the energy averaged over a wave, I'll call it E bar, was equal to gamma h squared over 8. And we had B there for considering different lengths of waves, or we could write that rho g h squared over 8. Let's consider just B equal to 1, so we have a 1 foot width here for our convenience. Then we can write that the average of the average wave energy is, I'll call it the average, then it's just the average of all these, rho g over h over 8 times the sum of hj squared, h sub j squared divided by n. Now we can rewrite question.
On the significant period, should that be big N or small n? No, below. Yeah, should that be big N or small n?
That's a large N.
That's the total number of waves.
That's the total number of waves in the sample that you took.
Total number or the total number of significant waves?
Total number of
waves or total number of significant waves?
total number of waves. The significant waves are just the highest 1/3 of the total number. So this is total number. The total number you count in your sample by counting across it.
So wouldn't you take the S off of there? Would you remove the S then?
What's that?
Should it still be T sub S? Or should there be
T sub S?
T
The
sub...
significant period?
Yeah.
Should it be the time of your sample divided by the number of waves in that sample?
Not necessarily significant waves.
Not the significant waves, the total number of waves. That's the, oh, T significant. Oh, I see your point. So that should be, this is the average T bar. So T significant should be the top 1/3.
Yeah, this is a small n. You had it like that when we left.
Yeah, so this should be, thank you. Oh, wait a minute, no, that's still not right. Because that's,
Isn't n defined just as a number of...
somehow I've gotten my symbols mixed up here. It's according to the short protection manual, it's the average of 10 to 15 successive prominent waves.
Prominent, yeah, significant.
Prominent wave.
Prominent doesn't mean it's highest. Prominent doesn't mean significant.
Average period.
I think we can define prominent as top third.
Thank you for catching that. And the prominent wave is just selected from the record like this. Got it? Mm-hmm. Right. Okay, so we can rewrite this one as log of probability h is greater than h hat equals to minus Oh, I need to rearrange that a little bit. Something isn't right. If I combine this one and this one, substitute this for HRMS and rearrange the logarithms, then I have minus HRMS squared minus Q times H hat squared plus log n from the end down here. And this has the form of y equals one, well, y equals x plus b. So you'd expect a plot that looks something like this, where you plot h over h hat over h RMS all squared against the probability that h is greater than h hat. On a log scale, have be a straight line with a slope of 1, and that's what's actually found. There's some scatter about it, but that's actually found. That's a verification of the Rayleigh distribution.
Would there be a 2.3 for the conversion of the log of the x exponential? It's not a natural log, it's based
Oh,
on...
sure, okay. And rather than put the like scale, or even a log scale, it should be 45 degrees. Well, that's actually what's found. And in the short protection manual, I'll show you a figure that illustrates that. Should have been right there. Well, I should have looked it up before class. I'll here it is. I'll pass this around. Well, to get something useful out of this,
Dr. Krone,
huh?
how do you define H hat, or how do you
H
define?
hat, it's the
what it
height
is?
that you select. If H hat is set equal to 0, then that's all the waves.
Oh, okay.
Just, if you set it at, well, I'm going to show you how to set it first for the significant wave height. Well, we can calculate the average of all the height of all the waves having H greater than H hat. I'll call it H of H hat. Lowest our protection matrix. And that's equal to the integral from H hat to infinity. H squared e to the minus H HRMS H hat squared divided by the integral from H hat to infinity. H e to the e to the minus H hat or HRMS squared. For H hat equals 0, this is always this integral turns out to be H bar is equal to 0.886 times HRMS. And for H hat, or for HRMS, let's say, H significant, that's what we want. It's equal to 1.416 HRMS. And this is very close to the square root of 2, so you commonly see H significant is equal to the square root of 2 times H RMS. And this is what we've been after this morning. This afternoon. So HRMS is easy to determine from your waves, from your wave spectrum. And presuming that if it's a cumulative Rayleigh distribution, then from HRMS you can directly calculate the significant wave height. It's just like standard deviation in a normal distribution. Any questions?
What does H bar equal in the second case?
The average of all waves. If H hat equals 0, that is, if we're considering all the waves above 0, then the average of all waves is about 0.9 times the root mean square value. And if you're considering only the highest 1/3 of the waves, providing the waves fit the Rayleigh distribution, then the significant wave height, the average of the highest 1/3, is equal to 1.4 times the root mean square value. And the root, I erased the root mean square value, but that's the sum of all. If you look at all of the wave heights, then calculate root mean square, the sum of all the h's. To n divided by n. So this is something that's easy to do. You just take off the peaks. I'm sorry. For a given wave, you take this difference, this difference, this difference, and so on to get the heights. And add them all up. For 15 waves, that's not much of a chore, you know, at a time. And then just multiply it by square root of 2 to get the significant wave height.
That's that h squared at sum there?
Oh, it's squared, yes, thanks. Okay, then the second one is the winds, which I said you get from the weather service. Usually you can get a summary of, I didn't bring one. Sorry, I didn't bring one to show you. You get a summary of winds from the Weather Service. It's just a table of winds, and it'll give the highest wind measured and the next highest and the percentage, you know, distribution. And the depth you get from navigation charts. Now, I should say another thing about depth. In tidal areas, the depth. I need help.
Sure, you could probably help. It seems like we have too many things that we know here. For example, you're saying we know the fetch for this case, or we're estimating the fetch.
Right.
And then,
And you know the wind speed?
right, and the wind speed. So that sets a point on the chart.
Right.
Well, how do you,
And that gives you for the fully arisen feed, and you interpolate between the curves.
right.
So we have
What is T then? The amount of time to wait to
Well,
travel?
the time, if it hasn't had time to reach the fully arisen sea, then you have to come back to the 30-minute. If it's only 30 minutes, then it's not, where's our 10,000 here?
Yeah,
Then you have to come back to the 30 minutes.
okay.
Yeah.
Along the wind stream, because we know the wind
Along
stream
the
is,
wind.
it never reaches the full fetch length. Okay.
Right.
So we started here, run the factor that we have, and then over to another time.
Well, as I'll describe on Wednesday, in most estuaries you have a tide to worry about. And as you can see, or if you play with those a little bit, you'll see that as the water gets deeper, the waves get higher. So that you want to consider the high tide case when you calculate the depth. Navigation charts are mean lower low water. And if you draw the tide, let's say this is mean tide level. You draw a tide, typically a diurnal tide will look something like this. But it will vary over a 2 weeks period. And the mean high water is the mean of all the highs. And the mean higher high water is the mean of all the highest tides during a day. And the mean lower low water, mean low water, and mean lower low water are the means similarly of the low, mean of all the low waters and mean of only the lowest low waters. And this is the one that the navigation charts give the depth for. So if you're interested in wave heights at a particular location, where especially in shallow water, in 10 or 15 feet of water, then you want to take into account the fact that at times the tide is high, and when the wind blows and the tide is high, the waves are going to be higher. So that typically you take the navigation chart and add the mean tide range or more to it in calculating the depth that you use in selecting the depth. If you're designing breakwaters, you also want to determine the runoff on the breakwater to determine its height, and of course you want to know that at high water. Well, I had all those copied so that you could go home and work some of the examples that they gave in there. Okay, I think that's enough to say about the waves in a
Question? Ray? When you determine what significant wave height was, well, how do we use that?
Oh, we started out talking about ideal waves, small waves, sinusoidal waves, and described the movement of the water by those small waves and wave height relations, so on. And I said that this theory doesn't apply to breaking waves, but it does apply pretty well, within about 10% actually, to waves, to real waves, if you use a significant wave height. So just use that same theory, but instead of height, h that we had in all that theory for energy and so forth, use a significant h. That significant height was first proposed by Monk, who's a physical oceanographer, and had quite a productive career. Then later, one of the faculty on our statistics group here, whose name escapes me right now, he's now at North Dakota State University, came up with this Rayleigh distribution. So that typically people either do what I described from a graphical record, or if it's on digital tape, then process it digitally and get the root mean square value and just multiply it by the square root of 2 to get the significant wave. Right? And the waves that we're talking about here are significant waves. So as long as you're careful not to deal with exposure, then you can use the linear wave theory. Now, if you want to dig deeper, there's a second order theory and a third order theory, and there's a lot of wave theories, and next higher order Stokes theory points out the fact that the circular motion of the particles in the water doesn't quite close. And as a result, or maybe in some cases more than closes, the result is that there's a net drift in the direction of the waves. I'm sorry, more than closes. So there's a net drift of the water in the direction of the waves, with friction, the viscosity in the water. And that drift actually transports material slowly. It's very slow, but it transports it slowly. So if you're really interested in that, you have to dig into that. If you're interested in waves in very shallow water, where the wave height is high compared to shallow water, then the waves no longer look like sinusoidal waves. They may look like sinusoidal waves out some distance from shore, but when it gets close, then they tend to have higher peaks and longer, shallower troughs, so that they become asymmetric, and eventually they get steep enough so that they break. And run on up on the shore. Well, these are called conoidal waves. So if you're interested in the details of what happens with waves where their symmetry is affected by bottom stress, then you need to look into conoidal wave theory. And that's, incidentally, that is described in the shore protection manual. I commend the shore protection manual to you in the later ones, because it's not only a good reference, and it gives references to the publications on which it's based, but it's written by people who use this day in, day out in their lives. So I've been through the process of preparing some of these manuals, and I can tell you they're very thoroughly gone into. So from a practical standpoint, they're pretty.
Does that give design guidelines? Does the manual give design guidelines? This manual, does it give design guidelines?
Is it?
Does it?
I have a cold.
Oh, I'm sorry. Does it offer design guidelines? The manual?
Is it? It's available in the government printing office,
Yeah.
and it's reproduced about every so often. It's updated every so often. The current update is, well, the last I heard it was supposed to be out in '95. Should be out. And they're brought right up to date. They have excellent library services there. Okay, what I'd like to talk about now is the threshold of movement under waves. And threshold of sediment movement under waves. And on Thursday, I'll pass out a couple of papers that describe for both non-cohesive and cohesive sediment. Yeah. From a consideration of the horizontal forces and the gravity forces or initially within the shield, came up with a relationship. And he said that the ratio of the shear stress, which is forces I mentioned before, to the gravity force, which is rho density of the particle minus the density of the liquid times G D to the Reynolds number, which Q's are D over nu, had a function that looks something like this. What he said was that this term should be a function of this term, the both dimensionless numbers. Then he made experiments and plotted the boundary between movement as near as he could determine. And this, you find this in text, any text on actually there's quite a bit of scatter. Any text on cohesive sediment cover. And the this is no motion, and this is motion or transport. And the curve is just a boundary between those two conditions. And it's useful because sure, if there's no motion of the grains, then you don't have to worry about transport at all. It's only when there is some motion. I think I've defined all these terms before, so no problem. And these numbers, this is about 0.03, for example. And down on these very small numbers, where the dimension gets small on the clays, this rises is sharpening because the particles are down on the viscous layer. They aren't exposed to the turbulent. Whereas out in this region, they're exposed to the turbulent. And then it levels off up here at about 0.06, if I remember correctly. Well, in the case of motion under waves, we have our motion. That is at the bottom, there's a bed. Up here, the water is moving in elliptical orbits, but on the bottom it just moves back and forth. And it does so with a zero velocity at this point, a maximum velocity in the middle, and then zero velocity in the reversers again. So the motion, if motion is going to occur, it's going to occur at this maximum velocity. If we call this distance here d sub 0, that is the distance. I've got my d's mixed up here. This is diameter of the particle, so let's make this a capital D. Then we have from our description before, the dimension of this at the bottom is equal to wave height by t times hyperbolic sine of 2 pi times the depth. I'm going to be in deep trouble here. I'll call it h over L. Well, we don't have a t here. That's the orbital length, and then the maximum velocity, call it u sub m, then is equal to pi h over t times the hyperbolic sine 2 pi. H over L. So we know the peak velocity here and the dimension of the motion.
What is lowercase h?
What's that?
What is this lowercase h?
That's the water depth. I've been using D in the past for this, but I've got too many D's here, so I call it H. Well, the same notions that were used for developing this curve, the ratio of the drag and lift forces, or gravity forces. A fellow named Paul Komar, whose paper I'll pass out to you on Thursday, found that using data obtained by others actually, that if you plot d0 over d, where this is the particle diameter here, out to the 1/2 power, and rho u sub m divided by rho particle minus rho liquid times g d. He found that for laminar conditions, that the data all plotted as a straight line. But that for turbulent conditions, which corresponds to this part of the curve, he found that plotted in a group that looks something like this. So that for this portion of the data, under laminar conditions, you can describe the threshold of movement as rho u sub n squared. This should be squared. This is just tau, rho u proportional to tau, divided by rho p minus rho l g is equal to a constant over here, a double prime b head times d0 over d. The 1/2 power. And he had, for one set of data, he has A double prime is equal to 0.392. And for, this is nanoharsh data. I'll give you this paper next hour. And for Bagnall's data, he had 0.211. From experimental data. Now, these data were measured in different ways, so it's not too surprising. This experiment consisted of a tank, just a water tank, about a foot wide and about 10 feet long. And on the bottom there was a platform mounted on rollers, and that was connected with a crank to a motor, so that the platform moved back and forth in a sinusoidal fashion, just like water does under weight. And he just increased the range or the frequency, either one, so that the velocity was greater until he saw motion. Now, when you look to see motion, you just watch the grains, and when you start to see grains moving, then you say, that's it. You know, that's a condition under which motion just starts. The problem is it's subjective, so different people see grains moving at different times. Bagnall, on the other hand, had an arc, a circular arc, that's about a foot wide here, and it was suspended from a pivot up here and driven by a crank that, you know, as it went around, so that this moved back and forth, and this was all immersed in water. so that it could move back and forth, and he increased the velocity until he saw the cranes move. So the fact that the experiments were different and that the people were different that observed it accounts for this, or can account anyway for this difference. Now for the turbulent region here, Komar said that let's consider the acceleration forces on the grains that are exposed to the turbulent motion. And he said that the ratio of the acceleration force to the gravity force is rho E sub m divided by rho sub s minus rho sub l g t. And he found that you could relate that on a log scale to d0 over d. This is log. To a curve that looked something like this. And he said that you can use his graph, which I'll provide you, to calculate the initiation of motion under turbulent conditions. So that he provided a way for this, and this he has data that plot. I'm sorry I don't have this to give out to you today. That you can use directly for determining the initiation of motion.
Ray? Does motion occur above the line? Is it the same idea as that?
No, in this case, let's see. Yeah, this is the initiation of motion, and for u sub m is greater than this value, then you have motion. Or you can say if the particle's less dense, then you would have initiation of motion. So it just describes, you know, if the value you find plots up here, then you have motion. If it plots down here, you don't have motion. So he provides a means of determining whether you have motion or not. The problem is, real problem is how to determine whether you're in the laminar or the boundary, laminar or viscous regime, so that you know which of these curves to use. And so he gives well, what he finds is, after a lot of discussion, is that if you compare the thickness of the viscous layer with the height of or the diameter of the particle, so we'll have d over delta, which is equal to the diameter of the particle divided by 6.5 times the kinematic viscosity times the period times 2 pi divided by 2 pi, 1/2 is equal to about 0.07 at the boundary. In other words, when D is larger than that, turbulent, and when it's smaller than that, it's laminar. And then he gives another one you're finding it d over delta equal to the diameter divided by the kinematic viscosity times the period time divided by pi, and 1/2 power equals about 0.3. And then practically, he says that if d is about 0.5, if the diameter is less than 0.5, typically they're in the laminar layer, and with more than 0.5, then they may be in a turbine.
Is that, what, millimeters?
Millimeters. I'm sorry. The application of this typically done for mean low water conditions, because the lower the water is for a given wave height, the more likely to move, and use the median annual significant wave height for calculating whether it moves or not. And yeah, that's about it. Well, that's all I came prepared to give you today. So we ran out like that.
This diameter here, what exactly is that?
The
0.5
diameter of the
millimeter?
grains,
That tells you what?
but
That's the diameter that was used in the calculations?
he said that typically, when they're smaller than this, then you may have laminar conditions. If they're larger than that, then you
That's
often
all.
have turbulent conditions.
All right.
Dr. Krone, sorry again. What was the point of the two equations above it, the .07 and the .3?
To determine whether, if the ratio of the diameter of the grain to the viscous thickness of the viscous layer is greater than 0.03, as defined this way, then it's turbulent.
Thank you.
I thought we discussed this business about the thickness of the viscous layer. If the grains protrude above the viscous layer, then you get eddies formed off them, and you get greater stress on them. If they're down on the viscous layer, then it's hydraulically smooth and there's less stress on them.